In episode 89, we talked about setting up interrupts and using interrupts, concepts of ISRs and enabling and so forth. Let's kind of clear all that up by using a real-world scenario, showing you how this is actually done in the real world. Of course, there's always the chance I'm going to make it worse. Now, what we're going to talk about is the Broadcom implementation of the ARM architecture that's used in the Raspberry Pi. Of course, well, there was a lot of words in there. Don't worry about it. We're going to touch on a couple of things that we have talked about in previous episodes, so if you've been following along, you should be good. Now, first of all, whenever it comes to the ARM processor, there are a couple of interrupts, and there are actually a bunch of interrupts, but there are three in particular that the user, that the programmer has access to in general. All right. First of all, there is the IRQ, which is just general purpose interrupts. All right. In an earlier episode in Polled.io, we talked about interfacing to the Broadcom free-running timer, a timer that just simply counts up, and we can actually set flags or set modes so that we can say, okay, a second has elapsed, and we can actually have an indicator that a second has elapsed. Well, you can associate that flag with an interrupt request so that you can be told or interrupted after a second has passed. Of course, there are also external interrupts. You could have lines, bits coming into the processor that whenever there's a transition from a 1 to a 0, or maybe a 0 to a 1, or just simply a level, they can interrupt you. That would be a hardware interrupt, some sort of an external device that says, hey, I need attention. That would be a general purpose IRQ. Now, there's also, though, a special type of IRQ called an FIQ, which is a fast interrupt request. All right, now, this fast interrupt request, let's go back to the original idea of interrupts. The idea of an interrupt is to asynchronously, at any point in time in the execution of code, have some sort of an external device say, I need attention, grab the attention of the processor. Now, as soon as that happens, if the interrupts are all properly enabled, you'll jump to an interrupt service routine, an ISR. And that routine will quickly handle whatever attention needs to be given to the external device that has interrupted you. So it's all asynchronous and it's all very quick. Now, in some cases, you want to have very immediate responses. Within a couple of assembly language instructions, be able to respond. This FIQ, this fast interrupt request, is designed so that you don't have to do some extra housekeeping in order to handle this fast interrupt request. Now there's a third kind, and this one, it kind of makes the hair on the back of my neck stand up whenever I write it up here, because it's not really an interrupt. It's called a software interrupt. Now, a software interrupt is not really an interrupt because I just talked about asynchronous, right? Could happen at any point in time in the execution of our code. A software interrupt really is no more than a function call. Remember, whenever a function or method, you're calling a routine. It is not asynchronous because it always happens at exactly the same point in time in the code. In fact, whenever we're looking at the assembly language instructions, whenever it comes to the ARM processor, it's an instruction like SWI. The Intel processor is int. Why is this included in the list of ARM interrupts? Because it does not call a method, a regular method. It's specifically set up to call an interrupt service routine. So remember, when we talked about interrupt service routines, we talked about how it's a different method from returning from a function than it is to return from an interrupt service routine, because the interrupt service routine oftentimes has to put things back the way they were. For instance, the processor flags have to be put back to the way they were. The specific shadow registers and so forth have to be put back the way they were. And the software interrupt allows us to call a function and rely on that putting back everything the way it was. All right. So those are really the three types of interrupts. Now the software interrupt, and for example, let me talk a little bit about the Intel one. In Intel, if you're returning to it from a function, you're using the RET assembly language command. So this is basically for a function return. In terms of an interrupt, an interrupt service routine return is RTI. And that'll give you one idea of the difference. And so if you called an interrupt service routine as if it were a regular function, when you hit this RTI, your stack wouldn't be right when you came back. Things would be all corrupted. So that's one of the reasons why we have to have that software interrupt. Now, before we dig too deeply into interrupts, let's also talk about something called the ARM modes of operation. Now, the reason why I'm bringing this up is because whenever we go from like, for example, executing code in a user's application to an interrupt, we're going to change the mode of a processor. Now, please understand that the modes, being in different modes gives the processor different capabilities, access to different resources. For example, the resources that are available to a user cannot be the same as the resources that are available to the operating system. For example, the operating system needs to be able to control a lot deeper into the functionality of the processor than a regular user application. So whenever we get interrupted, we shift these modes. So before we go into the specific implementation of the interrupt on the Broadcom processor, let's talk a little bit about the modes that are available to us. For example, there's user mode. And this is basically just general applications running, right? Now, and it's given some basic resources, but once again, you don't want to give it the low-level detail. In fact, this is one of the reasons why sometimes people find it challenging to program interrupts, because they're so used to programming in this mode and having access to a certain number of resources, they don't realize they have to shift down into a much lower level, kernel level mode before they can start accessing the resources that are needed for interrupts. There's FIQ mode, which is the mode that you'd use whenever you're going into a fast interrupt request. There's also IRQ mode, a slightly different mode, but it also is the mode that you shift to whenever you're getting interrupted, specifically with the IRQ. Now, the operating system, that one, and I don't know why I did that, the operating system runs in supervisor mode. So this one's basically operating system, all right? And that gives you access to a lot more resources than user mode does, all right? There is a mode called abort. Now, this mode, believe it or not, is another interrupt. So if you get interrupted with a fast interrupt request, you go to FIQ. If you go with a general interrupt, you go to IRQ. Abort is a special type of interrupt. Basically, it's whenever you try and fetch data or instructions fails. And we have to abort. All right. And what that's going to do is it's going to say, okay, we've got a special ISR we're going to need to call, a special interrupt service routine that we're going to call whenever we do get a bad fetch on data or code. All right. There's also undefined. Now, this one seems kind of weird. Well, why would you have a mode that's not defined? No, what you're doing is, this is what happens when you encounter an undefined instruction. Remember when we were talking about the general architecture of a CPU, we were talking about how the CPU brings in an instruction, and an instruction is just a pattern of ones and zeros. Well, what if we bring in an instruction and that pattern of ones and zeros doesn't match with any instructions that we know of? So it's actually an undefined pattern of ones and zeros, an undefined instruction. What does that mean? Well, it could mean a couple of things. It could mean that we're trying to execute from memory an area that doesn't contain code. Maybe it contains data, or maybe it doesn't contain anything at all. Maybe it was not initialized at all. We got to figure out what happened. We go ahead, and typically what you do is you terminate the application and you present an output to the user to say something like undefined instruction encountered, application aborted. It could also mean that memory got corrupted. There was code in there and memory got corrupted. Once again, you have to stop that application and tell the user that something has happened. All right. And there are a couple of other modes, but in general, this is kind of the list that I'm going to start with now. Now, one of the things that we talked about whenever we talked about going into an interrupt service routine is making sure that the application that we interrupted doesn't notice that anything happened. In other words, you can't mess around with any of the registers, none of the flags. Everything has to be put back the way it was. Well, the next thing that we're going to talk about is when you shift into one of these modes, how do we make sure that the values that were stored in those registers in the user application aren't affected? If we look at these sets of registers, what we see is that, once again, the ARM processor has registers R0 to R15. R0 and R0 down to about R12. Some of them have special purposes. They're handled a little special, in different special ways. But in general, what you're looking at is those, R0 to R12, those 13 registers. They're kind of general purpose registers. We use them to do, any sort of, accumulation, counting, things like that. Now, if you look at R13, R13 is actually our stack pointer. R14 is something called a link register, and a link register is where we contain the address that'll allow us to jump back from a function. So if you call a function, the place that you came from, and remember when we talked about the stack pointer, we talked about how we put that return address on the stack. Well, the ARM processor, if you keep nesting nesting function calls, you do use the stack. But in general, if you're just doing a quick call to a function and expecting to come back, what you do is you put the return address in that link register, LR or R14. And then R15 is our program counter, the one that points to the next instruction to execute. Now what we see here is in our different modes, we get different registers being stored, or not stored, but shadowed. And so, for example, in this fast interrupt request, it actually has a set of registers, R8 all the way down to our link register, R14, that we have a duplicate register. It's a separate set of registers. And those registers allow us to jump to this fast interrupt request. Remember, we've got to do things really quick. And so we are given duplicate registers in order to do our processing. And so we can do our processing in R8 through R12, not mess up anything from R8 through R12 in user mode. And that way we don't have to do any sort of pushing things onto the stack and slowing up things. But an important thing also to see is that the stack pointer and the link register, those guys also are shadowed. In fact, they're shadowed across all the other modes. That means that every single mode has its own stack pointer. So if we shift over to the fast interrupt request, we're not going to touch anything at all in the stack from our user mode. We're going to operate off of our own stack set up by the operating system. And then when we're done, we can jump back to the main code and not have touched anything at all in the stack in the main code. All right? Now, the reason why the link register is also being shadowed, we have a copy of the link register, is because when the link register is going to contain the return address back from where we interrupted. So our application code is executing. We get interrupted. The address where we got interrupted, that gets put into the link register so that after we finish up our interrupt service routine, we can go to that new link register, the one that is being shadowed, and we can jump back and not affect the link register that might have been in use in our main code. Those two things, the stack pointer and the link register, those two things are shadowed across all of our modes, making it so that I don't mess up anything in the user mode whenever I switch back to it. Now, if I need more registers, remember, I can't make it look like anything at all was touched. Any other registers I use, for example, in the fast interrupt request, R0 down to R7, any of those that I want to use, I do need to push onto the stack so that I'll protect those registers and then pop them back off the stack whenever I'm done with my interrupt service routine. Similarly for R0 down to R12 for the other modes. All right. Now, we talked about that last one, and so if you look in this bottom, we also are shadowing the processor status register, the CPSR. Okay, now remember the CPSR, that was a special register containing some flags. Now, in episode 83, we talked about special flags. There was the 0 flag, there was the negative flag, there was the carry flag, there was the overflow flag. Little indicators to say we just did an operation. Here's an overall set of indicators as to what the result looks like. Is it negative? Is it equal to 0? Did it result in a carry? Did it result in an overflow? Okay. Now, the ARM processor, it has a special, 32-bit, it's a big register that contains these flags. And so if you're looking up at the upper ones, let's see, we've got the negative flag, which indicates whether the result was negative. We have the 0 flag, we have the carry flag, we have the overflow flag. And you get all the way down here to the end, to the least significant bit sides of that register, and we have some flags that are, or some elements that are helpful to us whenever it comes to our interrupts. First of all, these least significant 5 bits. So what we got? 1, 2, 3, 4, 5. So bits 0, 1, 2, 3, 4. These are our mode bits. And so if you look at those bits, and you should get an idea from this table right here, exactly what pattern of 1s and 0s maps to which mode. So you can actually look at your processor status register, this CPSR, and you can figure out, if you look at the last 5 bits, exactly what your mode is. In fact, we can switch back and forth. Not going to get into it this time, but remember, each mode has its own stack pointer. What if I want to set up a stack pointer in my FIQ mode, but I'm in my supervisor mode? Well, all I need to do is simply get into my FIQ, set up the stack pointer, and then switch back to supervisor. So that is kind of how it has to be done. But it's kind of a little over what we're talking about today. All right. Now, there is a bit here for something called thumb mode. We're not going to worry about that right now, but there are 2 more bits that are vitally important whenever it comes to the execution of interrupts on the ARM processor. The first one is F, and this one enables, in the literature, it actually says it disables. So it enables FIQ. I'll explain how in a second. Basically, a 0 means that the FIQ is enabled. A 1 means it's disabled. That's why it's really called the FIQ disable bit, because putting a 1 there is going to disable that interrupt. And then we also have, I think the bit is called I. And this one enables our IRQ. And once again, a 0 is enabled and a 1 is disabled. And that's basically how you do those global enables. Remember, whenever we were talking about the enabling or getting an interrupt to work, then what we had were global enables. That's what these 2 bits are that are contained in our processor status register. And then we also had the local enables, all right? Now, it turns out that this is pretty easy. There are some assembly language commands that allow us to modify these, to be able to modify the mode, to be able to turn those guys on and off. But I just wanted to let you know that there's a register that handles all of this for us. All right? Okay. Let me make a little bit more room again. Now, in episode 89, we talked about in memory, there has to be a portion of memory that is reserved to list where to find each one of the interrupt service routines. Remember, it's hardware that's calling the interrupt service routine. So hardware needs to have an automated process that says, okay, this interrupt happened. I need to go to this memory location. It'll tell me exactly where to find the interrupt service routine. And one of the things that was important for that process to work was to have a portion of memory reserved with a list of the interrupt service routine addresses. It could have taken one of 2 forms. It could have been an interrupt jump table where each address was actually a jump to that interrupt service routine, or it could have been an interrupt vector table, an IVT. And an IVT, that was just simply a list of the addresses. So whenever you get an interrupt with an interrupt vector table, all you did was you loaded the program counter with the address in that table that corresponded to the interrupt that occurred. With an interrupt jump table, you loaded the program counter with the address of the table, the line in the table where the jump instruction was. Well, an ARM processor uses an interrupt jump table, an IJT. Now, at the very top of the interrupt jump table is the reset instruction. Now, reset is actually considered an interrupt. You don't return from its interrupt service routine, but it is considered an interrupt. And so this particular instruction, whenever you get a reset, whenever there's a reset on the processor, what happens is that you go to the offset into the jump table of 0, and that offset, whenever you go there, it will jump to the instructions or the interrupt service routine that will reset the processor, okay? The next one, at an offset of 4, remember, every instruction in the ARM processor is 32 bits long. That's 4 memory locations. So at an offset of 0, that instruction will be a jump to the interrupt service routine. It will take exactly 4 memory locations. So at offset 4, we have the undefined instruction. Right? So if you encounter an undefined instruction, 4 is loaded into the program counter, you execute the line, the instruction that is in this portion of the interrupt jump table, you jump to the interrupt service routine for an undefined instruction. All right, at 8 is a software interrupt. So there's where the location for the software interrupt is. At C, you have an instruction abort. So you've tried to fetch an instruction, and for some reason something happened in memory, you had to abort the fetch. You go to the instruction, you load the program counter with C, you go to the instruction abort. At hexadecimal 10 is the data abort. At hexadecimal 14, it's something called the hypervisor. So basically what happens is you get Whenever you're trying to do things in virtual machines, that's what is going to jump here. So anytime something is executed and you're in the mode whenever you're supposed to be working in a virtual machine, the hypervisor needs to be told they're trying to access some sort of a resource. We need to act as an intermediary in order to give them resources but not direct access. And then at 18 is our IRQ. That's our jump to our IRQ instruction. And then at 1C, that's our FIQ. And that's the bottom of the table. Now, remember what I said about the FIQ. That one's supposed to be super, super high performance. The reason why it's supposed to be super high performance is because there may be something that you only want to be able to execute just a couple of assembly language instructions before you start handling whatever event has occurred. The reason FIQ is at the bottom of the table is because all of these guys are going to be jump instructions. But the FIQ, what you can do is you can actually start you can load the ISR, the interrupt service routine, right there so that you immediately begin executing it. And you don't have to have that extra jump instruction in order to handle the FIQ. All right? All right. Now, a couple more things that I want to talk about, but before we go on to them, let me make some space on the board. Now, in episode 89, we didn't really talk a lot about something called an interrupt priority. Basically, whenever two interrupts happen at exactly the same time, which one do we service first? Because there is a responsibility by the hardware to pick one of those. And the programmer needs to be aware of which one is going to get picked first. Now, in terms of the ARM processor, at the top of the list, that is the that is the reset. And that is going to require priority 1. If a reset occurs, doesn't matter what else is going on with the processor, we're going to handle that interrupt service routine, right? Okay. Now, the next one is a data abort. That's the next in priority. So, if a data abort occurs, a reset would override a data abort, but a data abort, if it occurred at the same time as a fast interrupt request or a regular interrupt request or a software interrupt, the data abort, that would be the next one in priority. The next one is our fast interrupt request, so that's our third priority. Then we have a regular general IRQ, all right? Now, the next one is a prefetch, otherwise known as an instruction, abort. So that is a level 5. After that is our old friend, the software interrupt. And then the last one is our let's see if I can write this correctly, our undefined instruction. So there is our last, and in fact, the software interrupt and an undefined instruction. Understand that a software interrupt, if this were occurring, and I'm going to go ahead and I'm going to put a 6 here. For a software interrupt to work, an instruction has to be executed. Therefore, the instruction was interpreted correctly, so there was not an undefined instruction. If an undefined instruction has occurred, that basically means we tried to fetch an instruction and it didn't make sense. We couldn't decode it, all right? So there is the list of the priorities and, where they show up in our, how they show up on our ARM processor, all right? Now, let's just talk about the overall process. First of all, you need to have your interrupts enabled in the program status register, right? An interrupt needs to occur, and based on the priority, hardware picks one of those interrupts to occur. Now, the very first thing that whenever we talk about the process, and this is from the hardware point of view. And so the hardware, it's responsible for entering the interrupt, all right? Very first thing that it does is it saves the current program counter, all right, that's the one that's pointing, that's pointing to the next instruction to execute, in the link register for the correct mode. All right, so we actually have, if we've got a fast interrupt request, then it stores the program counter into the link register for the mode that we are going into. Then the next thing it does is it copies the program status register, and that's supposed to be a P, the program status register to the CPSR for the mode. That way, the flags are all, everything about what happened. Think about it. If we have some sort of an illegal instruction being executed, or something happens and we need to figure out exactly what was going on with the processor at that point in time, we go ahead and make a copy in the CPSR for the mode. And these are actually called SPSRs whenever it comes to the special modes that we're going into. All right. Now, the mode is changed in the SPSR. So for the mode that we're in, the program status register for that mode, we make sure that we change the mode to the correct bits. All right. Now, it is also possible that the bits that are identifying whether the interrupts are enabled and disabled, those are also set appropriately. But the next thing that we do is we execute the correct jump from our interrupt jump table, right? Interrupt jump table, all right? And so the very next thing that's going to happen is our ISR is going to be executed, all right? And that's really the responsibility, where the responsibility ends for the hardware. After that, the responsibility becomes the ISR. In other words, the interrupt service routine has to handle getting back. Let's talk about how the interrupt service routine gets back. Okay, now in the interrupt service routine, there's a couple of things that need to be done. But the main thing that needs to be done is we need to figure out what interrupted us. For example, the IRQ, that's a general purpose interrupt, right? There's a number of things that could have interrupted us. So we look at something called the interrupt flags to figure out or identify who interrupted us and what we need to do in order to handle it, all right? Now, at the end though, the very last thing that we need to do is we need to use the link register to return to the interrupted code. But there's a problem. Remember, way back in episode 85, wasn't all that many episodes ago, we talked about something called a pipeline. Now, the pipeline made it so that, first of all, it relied on us executing instructions in 3 stages. There was a fetch, there was a decode, and there was an execute. All right? Now, fetch is going to go to the address pointed to by our program counter to get the next instruction. So this one actually is, the program counter is pointing to the item to fetch. All right? Decode is decoding the instruction that we fetched in the previous cycle. So if the program counter is pointing to what we're fetching, then what we're decoding is what the program counter was pointing to 4 memory locations ago. So this was the previous instruction, which would have been at address program counter -4. All right? And then execute, we're going to execute the instruction that was decoded in the previous cycle that was fetched 2 cycles ago, which means that the instruction that we're executing is what the program counter is pointing at 2 instructions earlier, which means it is program counter -8. All right? This makes a problem when we're returning from an interrupt service routine, because if we return to the address that we are currently fetching or were fetching whenever we were interrupted, guess what? We're going to skip executing this instruction. How on earth is that going to work? It means every time we get interrupted, if we return back to PC, then what's going to happen is what was in the decode, that's going to vanish. It was as if it didn't get fetched at all. So we have to return from our interrupt service routine with a slightly modified value from what was stored in our link register. This program counter value was what was stored in the link register. Now, for a software interrupt, it was like a regular function call. So we don't have to do anything at all. We're just going to go ahead and return exactly to the value that was in our program counter. But for the fast interrupt request, for the IRQ, and for the pre-fetch abort, those three, we need to modify what's in our link register so it'll point back to the decode, which means we need to subtract 4 from the program counter so it's pointing to the appropriate instruction so we can refetch what was decoded, refetch it, and then start it on the process and start filling our pipe up again. That is pretty simple. It uses the subs instruction. Now, this is an assembly language instruction, but all it does is it subtracts a value, and there's actually 3 parameters. Let me go ahead and write the parameters and I'll point out what they are. So it'll be PC, that's the program counter, LR, that's the link register, and then the number 4. And so by doing this, what we're doing is we're saying from the link register, subtract 4 and put the result in the program counter. All right? Take the program counter, subtract 4, take the stored value, the stored value of the program counter in the link register, subtract 4 from it so that we're actually grabbing the address for the decoded instruction, put that guy into the program counter. Guess what the next instruction to execute is? It's the one that was in the decode stage when we were interrupted. Now, the cool thing about this instruction, this subs instruction, is that the processor knows that the only reason you should be doing this instruction is to return from an interrupt service routine. And so the processor also restores flags, takes care of everything, puts things back the way they were. All right? So there you go. We're just going through a couple of the details that it takes to implement an interrupt in the ARM architecture, specifically the Broadcom implementation of the ARM processor that's running on the Raspberry Pi. You'll probably never dig this deep, but it's a really good idea to see the things that get affected when we call an interrupt service routine and how they're handled with the CPU. We didn't get into all the details. There are a number of things we left out. For example, how do you locally enable, for example, the timer interrupt or a hardware interrupt? A lot of those things we haven't talked about yet, but at least you get a good idea of how the interrupts are handled in a real-world scenario.